I had to get a little fresh air there. Number 17, cobalt-121 is a radioactive substance with a half-life of 10,000 years. A radiogeologist finds 1.09 grams. He estimates the original deposit contained 33 grams. So I have changed this from my similar problem to be 56 grams. And let's keep the finding the same, 1.09. How old is the deposit? So half-life is mentioned. The formula for half-life is the amount after time passes as a principal times 1/2 to the t over whatever that half-life time is. So he estimates the original deposit is 56. That's your principal. The half-life is given in the text as 10,000 years. And he found 1.09. I'm going to do this by hand, all right? You can also use DI-84 if you have to. Doesn't really matter right now. The technique here is going to be to ln both sides. It's the easiest way to do these. Otherwise, you get some funky looking bases with logarithms. So we're just going to ln both sides. The natural log of 1.09 is equal to the natural log. Oh, too early. Forgot to isolate my base. And forgive me. Still early in the morning for me. Got to isolate that base. I don't want to write down whatever that is, a 10-digit decimal. I sure don't want to round. There's the fraction, okay? 109 over 5600. When you're dealing with half-lives of 10,000 years, just rounding a little bit will get you off by several years, so don't ever round. So 109 over 5600 is 56 times 1/2 t over 10,000. And now the technique is to ln both sides. Oh, I divided out that 56, sorry. That disappeared over here. This exponent goes out front. That's what we look like so far. We're going to multiply both sides by 10,000 to clear that fraction. We'll have a cancellation on the right. And now we're equal to t times the natural log of 1/2. And the last step would be to divide out the natural log of 1/2. Okay. I will probably put a small bonus here if you can clean this up. Because I prefer exact time here. I prefer exactness. But if I wanted to clean this thing up and make it look pretty, what I would do is I'd write it 10,000, set of parentheses, natural log of 109 minus natural log of 5600 over the natural log of 1 minus the natural log of 2. Now, like I said, I'll probably make that a small bonus on something like this. Just see if you can clean it up, because that's, you know, that's where we really want you to be. I need another set of parentheses there. 10,000 natural logs of 509 divided by 5600 divided by the natural log of 1/2 is almost 34,600 years. It's 34,597. There's your time. About 34597 years. Now, that cleaned up version, it's got to be equivalent. And hit that fraction key to type this thing in. 10, 1, 2, 3. Got the natural log of 109 minus the natural log of 5600. Close, close. Sitting over the natural log of 1 minus the natural log of 2. Milbrath made a mistake somewhere, didn't he? Wonder where I made the mistake. That's weird. Bummer. I wonder what happened there. I know they're the same. Let's try not using the fraction key. 10,000 times the natural log of 109. Oh, the problem was a typo up here, wasn't it? Ha, I got 56. I screwed up over here. I was supposed to type 109, not 509. This is my answer. 56,830 years. All right, let me go back to this where I made a typo. 10, 1, 2, 3. Natural log of 109 over 5600. Turn around and divide it by the natural log of a half. There we go. Typo. 56,830 years old. Let's see here. 18 is that ACT style stuff. So you're given some information about some logarithms and you're asked to do a couple things with them. And you're supposed to use these numbers, not your calculator, okay? Use these numbers. So you're asked to do log base 7 of 84. And you were given a 12 and a 4. Really makes me wonder where I got 84 from. Oh, I never changed these things right here. Okay, oops. I never wrote similar ones for parts 1, 2, and 3. So let's do a log base 7 of, I guess, 48. Here I'll do a log. That's what that was supposed to be. That was supposed to be a 48. Anyways, we'll just do a log base 7 of 48. To get to a 48 with my numbers that I have here, all right, I just think about 4 times 12. And I break apart multiplication with addition. So this is going to be 1.277 plus 0.712, which is 1.989. That's not hard. How do I make a 3 with a 12 and a 4? That's a log base 7 of 12 over 4. We break apart division with subtraction. And then we plug stuff in. So log base 712 is 1.277. We're going to take away 0.712. What's that going to give us? 0.561. I feel like that's right. Part 3, we got log base 3 of a 343. That won't work for the numbers I've got here. They won't even work for these numbers. So I need to fix this before I make you a printout. Instead of 343, what do I want to use here? We'll just do 64. Now that is log base 3 of 4 cubed, which is 3 log base 3's of 4. Oh, sorry. I need a 7, don't I? My assimilars are base 7. 3 log base 7's of 4, which is 3 times 0.712. And don't be that kid who's like, where is Milbrath coming up with these decimal answers? I have a calculator in my head, kids. It's pretty good usually. 3 times 0.712, what would you be? 2.46. 2.1, yeah, 2.46. Sorry. Almost messed that one up. 2.1, 2.136. I did about screw that one up. And that's 18. I'm getting tired now. 19, a similar question is f of x is the root of 8x minus 8, g of x is 3x minus 7. We're still going to find g of f of 4. We're still going to find that, okay? So f of 4 would be the root of 8 fours minus an 8. 8 times 4 is 32. You take away 8, I think you get 24. And that is going to be 4 times 6, which is 2 root 6. Now, you just found this piece. So now you do g of 2 root 6. So here's g. 3 times 2 root 6 minus a 7. 3 times 2 being 6. 6 root 6 minus 7. It says make sure you simplify your answer. And that's why I did simplification right here. So we got 20. Find all zeros of this function. First thing I'm going to do is I'm going to look at the graph. That's the very first thing I'm going to do. Oop, I'm also going to pay attention to what I'm typing in the calculator. I don't know if you were paying attention to what I did, but I wasn't paying attention to where my exponent was. Hit her with a good old Zoom 6. Oh, cool. This one actually has a touch. Touch is happening twice. It's at 1, by the way, isn't it? I bet if we look at the table, there's your 0, 1, 0. So what we have here is we have x equals 1 with a multiplicity of 2. I seriously doubt that yours does that. Yours is probably nothing but crosses. This one was just a touch. So I'm going to synthetically divide that out. This one didn't need any placeholders, neither does yours. And by the way, I'm dropping, I'm multiplying, and I'm adding. Sorry, I wasn't saying that. It's positive 17. And remember, this thing happened twice, so I'm going to divide it out again. Awesome. This is my remainder, my constant, my x squared. So the expression here is x squared plus 8x plus 17. There are 2 remaining zeros there, set it equal to 0. And if it factors, it factors. If it doesn't, it doesn't. That one doesn't factor. So I'm going to hit it with the QF. X is going to be opposite b, a negative 8 plus or minus square root of b squared minus 4 times a, which is 1, times c, which is 17. Sitting pretty over twice a 1. What's the net radical? I believe it's a -4. That's what it looks like to me. 8 to the second minus 4 times 1 times a 17 is a -4. Now the root of -4 is 2i. This will reduce. This becomes -4 plus or minus I. So what are my zeros? My zeros are x equals 1. It happened twice. I don't even care about the multiplicity. -4 plus I and -4 minus I. Now it says completely factor this thing over the complex number system. This one's kind of unique. It happened twice. Remember, it was a touch. Yours is not. Yours does not have a touch. I don't think it does. I'd be surprised if it did, but this one had a touch. So this one is x plus 1 written twice or squared. And then we take away. And if you take something away, you change its sign. So plus 4 minus I. This one will become plus 4 plus I. And there she is completely factored. 21, we're down to factoring. 2x cubed minus 3x squared minus 8x plus 12. The similar one, and actually much harder, is this one right here. 4 terms is a factoring by grouping technique. And if I just focus on the first two, I notice they have an x squared in common. If I pull the x squared, I'm left with 3x minus 2. Sorry, I was looking at something. I was actually thinking about if that was right or not. I make up problems. Sometimes I do it wrong. What can I pull from both of these pieces? I can pull a -4. And that'll make these pieces match. That's the big deal. These match. If I factor out 3x minus 2 from both terms now, I'm left with x squared minus 4. And this is why this one's a little bit harder. That still factors. Yours is not that hard. Yours is going to be pull and be done with it. You're not going to have that last step that I did. (22) is just factoring. You got a sum of 2 cubes pattern going on here. This is the a cubed plus b cubed pattern, where a is a 3x and b is a 4, because that's what it takes to cube and get those pieces. But a cubed plus b cubed factors is a plus b times a squared minus ab plus b squared. So I'm just going to throw everything into that form. A is 3x, b is 4. If I square a 3x, I get 9x squared. Take away the product, 12x. If I square 4, I get 16. And she's done. Your similar one here is 4x to the 4th minus 81. Needs to be changed. 16x to the 4th minus 81. This is the difference of two squares patterns. That's what this one is about, repeated use of the difference of two squares. So here, a would be 4x to the 2nd, and b would be 9, because 4x to the 2nd times 4x to the 2nd is 16x to the 4th. 9 times 9 is 81. So my initial factoring looks like this. 4x squared minus 9 times 4x squared plus 9. We got another dots pattern. Takes a 2x and 2x to make 4x squared, minus 3 plus 3 to make a -9. There is no a squared plus b squared pattern. Hundreds of kids have tried to create one over the years. It doesn't exist. That one is fine the way it is. And that's all those questions. I gotta hurry up and finish this so I can get to grading that take-home test y'all did.